All right, our second speaker is Himani Sharma. Now you can go ahead.
Hi, good morning everyone from Australia. So my name is Himani Sharma, as mentioned, and I am actually a postdoctoral researcher now. I joined last month at the Macquarie University in Sydney. So I would like to thank the organizer and of course the Association for Women in Mathematics to invite me to give a talk here. And so I'll begin the talk. First of all, I would like to say that this is actually based on a result that I proved during my PhD, but it's just included in the thesis and I have not submitted it anywhere yet. It's because the result at that point was not strong enough to warrant publication. But right now I'm working on improving this result, and I'll tell you what we have reached at that point also as well. So moving on to that, before I actually state what the result is, I would like to give you a little bit of motivation of why one would like to study square functions. All right. So see, square functions are actually have very fundamental importance in analysis, especially in the case of theory of complex function theory and theory of Fourier transform. But I would like to give a motivation in the theory of Littlewood-Paley. For that, we start with the function of R and we decompose it as summation pj times f over the set of all integers. Then where we take this pj as an operator, which is nothing but when it acts on the function, it's actually integral of the Fourier transform of the function f times the exponential here, which is actually the integral is taken over the interval 2 to the power j to the power j plus 1. So you can think of this as a dyadic intervals. So these pj's are dyadic frequency projection. We can actually say that this pjf represents the portion of f with frequencies with magnitude and the magnitude equivalent to 2 to the power j. Now, this can also be interpreted as Fourier inversion formula for if we take the function f to be in the class L2 of R. Right? So it was shown by Littlewood and Paley that for the interval p, for p lying in the interval 1 to infinity, we have that the LP norm of this function f is actually equivalent to an LP norm of the quantity inside the here, which is actually a square function. So we can have an equivalence relation between the function, the LP norm of the function, and the LP norm of a square function. So this is what we have, what we are seeing here. For p is equal to 2, we can see that this equivalence always holds, and thanks to Plancherel's theorem for that we always get the equality. Here for the equality in the sense, in fact, with a constant, so we'll get an equivalence relation for p is equal to 2. But for p not equal to 2, this relation can be think of as, you can actually interpret this as a substitute to the Plancherel's theorem for the LP spaces when p is not equal to 2. So this is where we come from for the motivation for square functions, how we can use it and how we can get a relation between the LP norm of the function. So square functions are also very useful in functional calculus. For that, we first define what is a functional calculus and then we move forward to it. Okay, so a functional calculus is something where we start with an unbounded self-adjoint operator on a Hilbert space, and we take omega to be a measure space. Then there exists a unique projection valued measure, ED lambda, such that we can represent the operator D as integral of lambdas, where the integral is taken over the spectrum of that operator D. Now, for a bounded Borel function, f, which is a map from functions which are taken from spectrum of D to the complex numbers, we can define an operator f of D as integral of f lambda, which are again taken over the spectrum of D. So this is actually the action of the function f over the operator that you can see here. So functional calculus is a map that takes the functions f from the suitable function class to a set of bounded operators on the space that we are dealing with. So this is what we have as a functional calculus. So what we are going to see is a characterization of square functions with holomorphic functional calculus. So what are holomorphic functional calculus? So for that, we start with a sectorial operator D. By a sectorial operator, we mean an operator whose spectrum lies in a sector, the closure of a sector. And apart from that, it satisfies the condition that lambda times the resolvent operator of the operator D is finite. The supremum of that is bounded. Now, if that happens, then with the help of a Cauchy integral form, with the help of the Cauchy integral formula, we can define the bounded operator as f of d is not actually equal to the integral taken over the boundary of the sector of the function f lambda times the resolvent of the operator d, where we take these functions in the class h1 sigma theta, and this is the class of those holomorphic functions defined from the sector of theta, defined from the sector to the complex numbers, which are L1 integrable with the measure d lambda over lambda. This is because the resolvent acts like 1 over lambda as it approaches to infinity. Yeah. So this is the class that we are dealing with here. This is how we define actually a Dunford calculus, but which can be extended to the class where we include bounded holomorphic functions as well. And from that, we define H infinity calculus. For the extra condition that we need for a bounded holomorphic functional calculus or H infinity functional calculus is that we take functions in the class H1 sigma theta intersection with H infinity. So together with that, if we have a boundedness of the operator fd in the class B of X, so I have not written, but if we take X to be a Banach space, then the operator norm of the operator f of d is actually bounded by the H infinity norm of the function. And in that case, we have a bounded holomorphic functional calculus or bounded H infinity functional calculus. So we are going to give a characterization of square functions with the boundedness of the holomorphic functional calculus. So this was given in early 90s by Cowling, Daust, McIntosh, and Yagi, that if D has a bounded H infinity functional calculus, then we can have equivalence of this square function with the function with the element of the space that we are taking here. So we can get this characterization here. In fact, this holds the other way as well. But for that, we need to have that the operator is in fact not just sectorial, but R sectorial, and it satisfies this square function condition. So if we have that, then we have a bounded holomorphic functional calculus. So what is R sectorial? R sectorial is an operator, like an operator is said to be R sectorial if the supremum here you can see, if we take the set of all lambdas for which this quantity is finite, we want that set to be R bounded. Now, I'm not going into the detail of R boundedness here, but R boundedness is something taken to be which is stronger than boundedness. And you need some Rademacher sequence, which is the sequences of plus and minus 1 with probability of them occurring as half. So if we have that, then the operator is said to be R sectorial, and together with the square function condition here, the equivalence of the square function, we get the boundedness of the H infinity functional calculus. Now, this is what we have. Another important ingredient, I would say, in the study of square functions is the Riesz transform operator. So moving on to that, Riesz transform operator here is the nabla times delta square root of delta, but you can also have an operator of the form nabla L to the power half, where L is taken to be a self-adjoint operator, non-negative self-adjoint operator. And usually people also take L to be as operators. Here I have taken just the Laplace operator. It could be a Schrodinger operator with non-negative potential as well. Okay, so I'm going to work with the Laplace operator only. So we are going to see what is a Riesz transform? Oh, sorry, this is a Riesz transform. What are the conditions that we have? Why do we study Riesz transform? And some boundedness on that and their equivalence with the square functions. Yeah, so boundedness of Riesz transform on LP allows one to define LP-based Sobolev spaces using functional calculus of the Laplacian. So this means that when we need to define LP-based Sobolev spaces, we are going to make use of a Riesz transform operator. But how are these useful in that case is, if we take M to be a complete non-compact Riemannian manifold, then there are two obvious seminorms to define the Sobolev spaces for functions which are in LP of M. Now, these norms, seminorms are, first is the nabla of F, which is the gradient here. So this is actually local and more geometric nature. This is of that form. And another seminorm that we have here is the square root of the Laplacian. If I'm not wrong, it should be to the power half. Okay, yeah, it's not minus 1/2. All right, once we have this, this is more non-local and more analytic nature. Then we will be able to define the Sobolev spaces here with the help of these seminorms. Now, if we take our M to be the Euclidean space, then we have an equivalence here with these two seminorms for every F in the class C0 infinity, smooth and compactly supported class. So where the second inequality you have here is actually giving you the boundedness of the Riesz transform. So that is how the Riesz transform, boundedness of the Riesz transform is taken into play. Okay, with the help of these two seminorms. So once we have that, yeah. And so the second inequality, the first inequality comes from the fact of duality, that we get this equality relation here with these two seminorms to define the Sobolev spaces. Now, this is the case when we take M to be Euclidean space. But the question arises, for which complete non-compact Riemannian manifold M does the above relation hold? So if we take, all right, if we take P is equal to 2, then we have the equality throughout. And if we have, if the P is not equal to 2, then the relation, I mean, getting such a relation for M is not at all trivial. And a lot of work has been done throughout, where this, I mean, you can actually either have a restriction on the range P or on the manifold to obtain such kind of relation, or to obtain boundedness on the Riesz transform. So that we are going to see here what all has been done throughout, but maybe I'm going to take only a few examples of it, but not all. And let's see what has been done throughout now, till now. So it was done in 1999 by Kuhn and Jong, that on LPM, if I take M to be a complete Riemannian manifold, and for the range P in the interval 1 to 2. So the bounded Riesz transform has been shown to be bounded for M, which are complete Riemannian manifolds, satisfying some conditions. And what are these conditions? It means first we have a doubling volume property over this Riemannian manifold, which means that you take a ball of double the radius and you need C times the ball of a radius 1 to cover that ball. So this is how we define a doubling volume property. And the second condition is that the Laplace operator, since it generates a heat semigroup, we have to see that the heat kernel associated with it has an upper estimate. So this is what the additional condition they needed. So on this space M, LP of M, they showed that the Riesz transform is bounded for the range P in the interval 1 to 2. Later in 2001, they also proved the boundedness of the Riesz transform for P in the interval 2 to infinity, the remaining part of it. But apart from assuming the above two conditions, which they had for the case P in the interval 1 to 2, they also assumed that the heat kernel has an upper estimate on one forms as well. I'm not going into the detail of one forms. You can check what it is there in their paper. But this is what they have done for the range P in the interval 2 to infinity. So if you see here, both the cases, or in fact, many other results that have been done so far, they have assumed the function, the space, or the M that they have taken, the manifold, has doubling volume property. So not many results have been done so far, which includes the non-doubling case. But in 2019, Hassel and Sikora considered a special case of the non-doubling manifold, where they considered this manifold to be a connected sum of Euclidean spaces, which are of the form Rn1, like Rni cross Mi, where each of these Mi's are compact manifold. So this manifold is also called manifold with ends. So here we have Ln's, which are all greater or equal to 2. So on these manifolds, they have shown the boundedness of the Ries transform, but the range of P is being restricted to 1 to the minimum of the number of the Ni's that we are taking, or the manifolds that we are taking here. So once we have that, we actually get the boundedness of the Ries transform for the case of non-doubling manifold. Yeah, it's a particular case of that. I would not say that it's cover all the entire range. That includes the Riemannian manifold with non-doubling property, but no. Okay, so before moving on to our main result, we'll now see what are the types of square functions that we have here. For that, we start with a classical Littlewood-Paley G function. As we saw from the Littlewood-Paley theory, we will have a characterization with the function and a square function. So this is what we get from a Littlewood-Paley G function, that we get an equivalence, which is a square function estimate on LP of Rn. So this square function we have here is actually a simplified form or a simplified version of an abstract square function estimate that we get for the operator, for the Laplace operator here. And so we have, so this is actually a square function with respect to the time derivatives. So a square function that comes with respect to the time derivatives is called a horizontal square function here. And this is the more general form of it we have, which is actually given in terms of the semigroups that we are dealing with. So we are going to represent, since I'm going to use this QH later, I'm going to write this GH function here, or GH operator, as something which is QH of f of xt, where this f of xt is this operator, t delta e to the power minus t delta f of x. So yeah. Now we have this square function operator with respect to the semigroups. So many mathematicians have actually used a resolvent form of this square function as well, which we have here. So this is a square function operator, which is a horizontal one. And we are having here, this is the resolvent operator that we have here. So this is taken for every m, for some m in the range n star. Yeah. This is the horizontal square function. So we can also define another square function operator, which is called a vertical square function. And this is done with the help of space derivatives. So again, we are defining another interval, but the only difference here is that we have a nabla here. And instead of having the same power as this, we always take a power less than that. Okay, so when we have this square function operator, we can actually have another operator in terms of the resolvent, which is given in this particular way. So these square function operator, so in both these cases, it can be seen that we have square function in terms of the semigroup as well as in terms of the resolvent. So it can be seen that there is a very I would say that these two are kind of equivalent relation, but not always that is true. So it is still possible to get an equivalence from the semigroup to the resolvent operator, and which can be done by obtaining boundedness of the holomorphic functional calculus for the corresponding Dirac operator in case of the vertical square function, and the case of Laplace operator in case of the horizontal square function. So with the help of that, we can actually go from the exponential to the semigroup to the resolvent case. So another square function that we have here is a conical square function operator, which is kind of little different from what we have for the horizontal as well as vertical, because it is taken over a cone. And this is constructed by Lusin's area type integral. And one way of writing them is for the Heath semigroup is the following way. So they are also very closely related to the 10th space norm and are used in many applications. For instance, they can be used to extend the theory of Hardy spaces in a way that is suitable for operators beyond the Calderon-Zigman class. So also it can be, they are actually very useful in the sense that they are mostly useful in concrete situation, whereas the vertical ones are useful in abstract situations. But what we are going to deal with is mostly the horizontal and the vertical square function. We are not going to work with the conical square function at the moment. So I'm going to talk about more results that have been done in the case of horizontal and vertical square function operators. Okay, on the space LPM, where M is any generic metric measure space, whether doubling or not, it has been shown that both the forms of the square functions, which was the horizontal square function in the semigroup form as well as the resolvent form, they both are bounded on LPM spaces. And this has been proved by Stein long back. I think it was, if I'm not wrong, you can see it in 1956 book. I don't know. I don't remember the book name, but you can see in the references later. Yeah, so that result has been shown for these two horizontal square functions. And this has been done for every M in the generic metric measure space. So we do not have to worry about that later, whether we are going to restrict the domain of the, restrict the manifold or do something on it. It has been done. Recently, a new proof was actually given by Bailey and Sikora for the resolvent form of the horizontal square function, but they have actually given it for a particular class. So it's nothing new in that sense, in the sense that it has already been proven, but they have given a different proof. And that different proof comes from the way they have actually given a proof for the vertical square function as well. But their proof is true for the Riemannian manifold with ends that we have seen before, how they have defined as a connected copies of L Riemannian manifolds. Yeah. All right, so these are cases for the horizontal square function. So for the vertical square function, Cohen, Zhong, and Lee, they proved in 2003 that if M is a complete Riemannian manifold, whether doubling or not, it was done for both the cases, but for the range P lying in the interval 1 to 2. So only this case was considered, and they showed that the vertical square functions, which with the help with the semigroup form, is actually bounded in the on LP of M spaces. Later, it was also proved by Cohen and Zhong that for P in the range greater than 2, if M has doubling property and the heat kernel satisfies Gaussian upper bounds, then only we will be able to get a boundedness of the vertical square function. So in those cases, if we see this Q plus here is actually the set of all P for which the Ries transform is bounded for on LP of M spaces. So once we have the boundedness of this Ries transform here, we'll be able to get the boundedness of the vertical square function, but for the range 2 to Q plus only. And this was proved for doubling metric measure space which satisfies this Gaussian bounds. Now, this result so far has been done for the vertical square function, but only for the doubling property with the manifold with doubling case. So for the non-doubling also, not many results has been done so far, but recently, including that paper, this 2021 paper of Bailey and Sikora, they actually showed the boundedness of the vertical square function for LP of M spaces, where M is a manifold with ends that we have seen before. This is a case of a non-doubling manifold. So this is not, in fact, a general result, but it includes the case of non-doubling manifold. It's a particular case of that. So they showed it for the Ries for square function with the resolvent operator, and they tried to break the integral into lower and higher frequency part, and they proved it using that fact. But since Andrew Hassel and Sikora has proved boundedness of the Ries transform for these manifolds, they use that fact to prove the boundedness of the vertical square function here. So this is taken from the fact, the previous one here, as we need the boundedness of the Riesz transform to get the boundedness of the vertical square function. So this is what they have proved here by using a result by Hessel and Sikora, which was the boundedness of the Riesz transform. Okay, so moving on to our result, what I proved during my thesis, and I'm bringing back the characterization that we need is from holomorphic functional calculus, boundedness of that to the square function. So the result that we gave here is actually for a general metric measure space, irrespective of whether it has doubling or non-doubling property. We tried to assume that, we assumed for that the operator, the Riesz transform operator, is bounded on LP of omega, where omega is any general metric measure space, and delta is assumed to have a positive, generates a positive contraction semigroup on LP of omega spaces. Then if that happens, then we can control the vertical square function operator by the horizontal one, which is further controlled by the LP norm of the function f. But the result here is on the LP L2 spaces. So if you see this part here, the square function, this can be think of as the LP L2 norm of psi TD. Yeah. This is the LP L2 norm of the function. So we have the L2 norm inside and the LP norm outside. So this is how we define the LP L2 norm. So we are saying that the vertical square function is bounded by the horizontal and the remaining holes. So for this, we need the characterization that we have above and see how it is done. So since the operator delta generates a positive contraction semigroup, it has a bounded H infinity calculus. This has been proved by Carlton and Weiss in 2001, that if that happens, we'll get the boundedness of the operator, the H infinity calculus boundedness. So once we have that, we can be able to apply the characterization that we have above. And once with the help of this characterization, it means we can start with QH. So if you recall, our QH was integral T delta e to the power minus T delta f of x whole square dt over t and whole to the power 1 over 2. So this was with the Laplace operator here. Okay, so this is actually, so the Laplace operator that we are taking is the Laplace-Beltrami operator, because we are dealing with general metric manifold, metric measure space. So how did we get from the QHF to the F is nothing but the operator that we have in QHF, we can think of as some psi TD, and we can check that this function psi will belongs to the class H1 sigma. So once we have that, we'll be able to get the boundedness here as from the characterization that we have above. Now, once we get this part, we need to show that the vertical square function is also bounded by the horizontal one. And this is in fact done with the help of a gamma multiplier theorem, which shows that if initially the operator is bounded, and if the set of those operators is actually R bounded, then we will be able to get the boundedness from the LP-L2 norm. So here the operator is just a single operator, which is the Riesz transform operator. So any single operator or a set of all single operators is always R bounded. So we can see that once it is bounded, it is R bounded in this case. And with the help of gamma multiplier theorem, we'll be able to get that this Riesz transform is bounded on LP of L2 spaces. Again, once we have this boundedness, going from vertical to horizontal square function is just play with the numbers, with Laplace and Nabla operator, that we'll be able to see that we can move from the boundedness of this operator, vertical one to the horizontal, which can be possible easily with the help of the boundedness of the Riesz transform operator. So this gamma multiplier theorem is actually, can be think of as a linearization of square functions with the help of randomization. As we said that we need R boundedness there. In the discrete case, it can be think of as Khinchin-Kahan inequality, if you have heard about that. And in the continuous case, it can be think of as Ito isometry, extension of Ito isometry. Yeah. So this was the result that was proven already and is there in the thesis. Now I'm trying to prove the reverse part of it. What if like this relation here holds, then can we get the boundedness of the Riesz transform here? Now, I'm not able to get exactly what it is, but we have been able to see some of the part if it can be possible or not. So the reverse of the theorem, can it be true? Maybe, but to certain point where we have tried to restrict the range as well of P, as well as some relation on some conditions on the manifold that we are dealing with. So some of the result that we get, so this is in an abstract setting. So some of the results we have been able to get from the results that have already been proven. So it was proven by Comets and Uhabas that the GV here, if you see, sorry, not GV, QV here, this is the vertical square function. So the boundedness of this actually gives us the boundedness. In fact, they showed that QV is bounded if and only if they define a set GP, which is something like T delta square root of T delta e to the power minus T delta, a set of all those T's for which this operator is bounded, or GP is a set like this. So once we have this condition, they showed that the boundedness of QP implies boundedness of GP, where GP is the operator as square root of T nabla e to the power minus T delta. So if this GP is R bounded, or the set of all these operators is R bounded, then we have the boundedness of the vertical square function. So there is a relation. In fact, there's this in the result, in the paper by Osher, Cohen, Zhang, and Hoffman, they actually showed that for M, which satisfies doubling volume property and L2 Poincare inequalities, then for the range P in the interval 2 to infinity, the boundedness of GP implies boundedness of the Riesz transform. In fact, this relation is also, I think, if I'm not wrong, this is also an equivalence relation that we can get the boundedness of GP. The boundedness of GP will give you the boundedness of Riesz transform. Now, since the R boundedness is a stronger assumption or a stronger property than boundedness, so R boundedness of GP will always implies boundedness of GP. So once we have that the vertical square function is bounded, we'll be able to get that GP is R bounded, and the boundedness of GP will give us the boundedness of the Riesz transform. So this has been done for P in the range 2 to infinity, although I have tried to see what has been done so far. For the range 2 to infinity, for M satisfying doubling property. So the case of non-doubling is still not being done so far for the back case, moving from vertical square function to the boundedness of the square function. So what we need to try to do is to reduce down these assumptions, or to prove boundedness of Riesz transform with the help of boundedness of the vertical square function for the non-doubling case. And this is what I'm waiting to do, or I'm currently working on. All right. So here are some of the references that I have seen. All right. Thank you. Oh, my last slide is not there. Okay.